Hi there, welcome back to our segment called Happy Trees. Today we're going to be painting with a couple different colors. We're going to have them go down at the bottom of your screen while I'm talking. In particular, pay attention to that alizarin and crimson because it's important to get the right kind of lizard for the right kind of crimson. Today we're going to actually do a little bit of Dick Van Dyke Brown in here. We're going to finish that painting that we started last time. Oh yeah, that's a happy little tree. All right, let's go ahead and dip our brush into the grass. It's natural that way. And we'll just beat the devil out of this feather. That should do it. Now our brush is happy again. Let's go ahead and finish this up. Got a little bit of Pythagorean blue or something. And I think that should just about do it. Good job, everybody. Hope you're having a happy day. Let's get started for today. We're going lecture 7 today. This is the last bit of kind of circuit stuff before we start integrating our knowledge of ODEs into circuits and then developing into our transform lectures later on. So this lecture is like the culmination of everything we've done up to this point. It's like a little temple, if you will. It's the operational amplifier, our good old op amp that we started with. We've come full circle, and now we're going to construct this beautiful temple that we're going to enjoy for the rest of our adventure. So we're going to build our op amp in terms of the MOSFET tools that we've developed so far. We want the following things. We want a lot, okay? We're very needy. We've got to have some high input impedance, large differential gain, a low output resistance, and the ability to source a large amount of current. We want it all, okay? And we're going to get it all because of the op amp. It's like a magical, mythical place that we're going to here, and I guess you could call it like our temple of time, right? So this is our real op amp, right? Oops, that's really thick. Let's calibrate our pens today. This is our real op amp. I'm kind of, my age is not as young as you guys, so I grew up on this one, and in fact, it's a good resolution for what we're kind of doing today. So, good enough. We're gonna do the good enough version of the inside of the op amp today, but keep in mind, it's always better than where we started. Okay, this is like where we started. All right, let's get into it. We're going to build a handy dandy block diagram first. The book does not have this. I'd like to add it in, hopefully in the next edition. A couple of things really quick before we really dig in. As far as the book's concerned, I know I talk about it constantly, but instructors kind of press you a lot for the teacher reviews. I don't care. What I would like you to review, though, is the book on Amazon if you got it. We only have one crappy review, which I'm sure you saw. It wasn't even a class that Tom or I was teaching. So it's, I don't want to complain and say it's not fair, but come on, guys. Can you give me some better feedback than that now that we're actually utilizing it in the course for this section? So it'd be great if you could go on there and review it. Be honest, I don't mind criticism. I have no shame, and so no worries there. And I hope y'all are enjoying it so far. And any of you guys that buy the book this semester and down the road, you kind of want an update or something like that, I'd be happy to send you the PDF version of the most recent thing for anyone that's, kind of a verified purchaser. And I've done that with a number of you so far that, you've purchased the book and I've given it to you on the condition that you just don't share it or just, disseminate that material, which is fine. I mean, that's what it's kind of all about. Like we need a little bit of bread to keep ourselves fed, to keep developing this thing. But other than that, we're not really looking to make $1 million here. So far, I think total sales on the book is totaled like $500, which sounds like a lot, but actually it only funds us for like part of a summer for doing like a TA to help develop the text a little bit further, do a lot of the editing. There's a lot of work that goes into it. So thank you guys so much for your support so far. All right, with that, let's go ahead and do something that's not even in the book. I've got a lot of work to do. Okay, let's color code this thing. I love doing proper color coding. Yeah, maybe I need to turn up the pickup on this pen. All right, we got the current mirror down here. All right, and our differential amplifier, we'll do an orange. And this guy is actually constructed from what we call a differential pair. And we're going to do a kind of a two-stage example of how we build this thing. The next one you're more familiar with. It's our good old CS amplifier. And finally, we end with, as promised, a common drain amplifier. Because we need to pump out those amps as current. All right. So flows like this kind of. And then our output, our final V out is over here. And then I'll give it little antennas. It's cuter that way, right? And we have VN minus and VN plus over, VN plus over here. All right, so this is our basic construction. It's typically about 10 transistors or more. And that's why I say today we're kind of doing the low res version of it, right? Like we're not quite going all out here. This is our first time constructing an op amp, so we don't need to put all the bells and whistles in here, but we'll get it good enough that you can understand the inner workings. So our differential amplifier here is going to be the first thing we talk about today. Then we'll move into the current mirror, tack on that CS amplifier, and finish with the common drain amp. Our first thing here, the differential amplifier has high input impedance. And it provides our baseline VD equal to VN plus minus VN minus. And this is the thing that we're amplifying. So whatever we stick in, what we get out is the amplified version of this. Our gain is applied here. So that's our comparison. And it's going to be, with respect to V out. So V out over VD, our final V out over VD is going to give us our amplification of our signal, effectively. Or whatever it is that we're looking for. So yeah. Next thing is our current mirror, and this is biasing the current for the differential amplifier. All right, and the CS amplifier provides big gains. All right, we do get some gain in here too, but it's the combination of our diff amp and our CS amp that really give us that crazy amount of gain that we need out of this system, that we need out of the op amp. Of course, we can't have that unless at the end we get that RO, but we just want a little bit of RO, and we really need that high current capability. We can't go anywhere after this, so we don't have any current after we've done all this. Okay, so here it is all laid out for you guys. I've already scribbled all over it for you because this is not the first take. But this is it, all laid out for us. So as we move through here, we're going to kind of check the boxes as we go. One little update here. I added these charts in to the lecture slides. I'm adding this little bit in here so that you can pause the video and come back to this and look at these equations because they come in rather handy as I'm discussing this throughout the lecture. In particular, we'll use things like this guy here. Oh, that's a big marker. And, our gain calculations and things like that, like these equations here, all these different gains. This guy here, whoops, I gotta fix that in the book. Sorry about that. But yeah, just here for your reference. I'm yammering so that this is up for a minute so it's easy to find and pause. All right, let's keep going. Okay, let's talk about our differential amplifier stage. So this is our first input stage. Okay, so it's going to produce our first output, if you will. All right, it's taking in that differential between Vin plus and Vn minus and spitting out a V out, from which we will use a lot. All right, so let's draw out a simplified version. This is just a differential pair. And for this, it's going to look similar to stuff we've seen in the past. V plus up here, two resistors. We'll call them RD for right now. Then we have our two MOSFETs. And they're connected to our out leads. So we have VIN plus and VIN minus. These guys come together. There's a current bias down at the base. We'll call it, apparently I can't spell. I bias, not base. And here we go. We have V minus down at the bottom. Okay, so first note. Note to bene. V out is really... Oh, we didn't even draw a V out, did we? Let's put that in there. There we go. V out. I know this is kind of violating the notation we did before where we just had I's and O's, but that's okay. All right. So V out is really more a function of V... That's not a V. VGS plus and VGS minus, okay? And those potentials live minus here, plus here. There's VGS minus. There's the plus. Here's the minus. VGS plus. So that's an important note here because although we're taking in, VN and VN minus and VN plus, it's really more a function of VGS, as we'll see. Okay, so I bias here is just the sum of ID1 and ID2 running through here. And that should be pretty clear. We have two currents coming down here and here. This one's ID1, this one's ID2. Then these two add up to get, come to my I bias. And I bias is governing the total sum of those two currents. Here we go, steering. So what do I mean by steering? Well, if, let's say, Vn plus is greater than Vn minus, okay? Then what we have here is the potential VGS plus has got to be greater than the potential VGS minus, right? So what we end up with, let me write that up here real quick. What we end up with then is that ID1 ends up going greater than ID2. From here, we can see that our input voltages are essentially steering the current in our transistors. Note that our total current, I bias, is fixed, more or less. Therefore, we have V out is increasing as this difference here is increasing, because there's less of a voltage drop over RD. So you can take a minute here and kind of work some of this out for yourself if you like. You know, pause the video and do some work. There's going to be a lot of that in this particular lecture, so take your time with this lecture. You know, there's a lot to digest in here. I don't want to say none of this material is going to be in an exam format. There will probably be small pieces of it, but the entire enchilada will probably not be its own question on a quiz or final exam. But you should be familiar with how all these pieces do come together. Another thing to note here, so we have no current flowing through gates. This is kind of obvious, right? I mean, we know that. Currents don't flow through gates. Well, the thing that this does, though, is that it validates our claim that Rn is effectively infinite, right? We have infinite input resistance because our input terminals here are not letting any current through GD or GS, which is good. Otherwise, our transistors would be broken. So if we look, though, at output of this, what do we end up with? Actually, I'm going to move this bit over here. Okay. So let's look at our output, V out. And I'm not going to make it equal to. These equations can kind of get complicated. We're not even doing the full op amp, right? This is just a model of our op amp, and there are going to be some pieces and stuff missing anyway. So we'll just kind of approximate here. This will get us close. GM VGS plus minus VGS minus over 2 RD. So note here that the GM is consistent between our two MOSFETs here and here, because we're assuming they're kind of pulled from the same batch and everything, so we're good on that. If we take our V out now, we can actually calculate our gain. And this is the big theme of the day, is gain. I mean, it is an operational amplifier, right? So that's all we really care about at the end. So AD is going to end up being proportionate to GM over 2 RD. which we can rewrite as, K I bias over 2 RD, all that good stuff. And actually our RD, we're going to replace these with, MOSFET. So this is actually going to get changed a little bit too. And at the end of it, we're going to end up with a gain that's on the order of 10 to 100 from this stage. So effectively, this guy's going to turn into a little RO, right? So when we go to design our differential amplifier stage, you can see the replacement in here of those resistors with these transistors. So at the end of the day, we end up with this for our gain factors. So those resistors, those resistances are helping increase our amplification even further. So this is our more realistic device. Okay. And we call these our active loads, of course. And to connect up, there we go. I actually lined them up pretty good. This is our I bias right here. So when we're looking at this circuit, we're connecting in these two pieces together. This part's our current mirror. And this part here is our diff amp. Okay, so our current mirror is governing the I bias for our diff amp. This wire here, I'm going to do it in we'll do it in green. This is non-intersecting here. There's no node. So keep that in mind. We're not tying the gate and the drain together on that one. But this is going to connect over to our one of our other stages later on. So just be aware. Be prepared. Okay. What else do we have for this? There's not much else to talk about here for the current mirror. We've already discussed how these function. One note is that this could actually be represented by 2 MOSFETs, and for those, their drain leads are tied together, while the gate leads are also connected, and source leads are also generally connected. So effectively, they're parallel for the 3 lead elements between these 2 and 3 here, if you wanted to draw it out. But it makes it kind of messier, so we're not going to deal with that. The book has a pretty good description of these guys here, and it gives us what is effectively pulling 2 times IREF over here for our bias. So no big deal. Alrighty. So we've replaced RD with Q10 and Q9 actually as well. This serves as an active load. So again, we have this, just to reiterate, RD goes to R0. So our gain equation, recall gain was proportionate to, in our previous lectures, what would be RD in parallel with RL, in parallel with little RO6, the AC output resistance of this MOSFET. Now we're going to effectively show that we can get rid of this guy, and this guy obviously gets replaced with RO10. So RL here, the output is tied to gate, so no current there, and I'll show you guys where that's going in a second. And capacitor, which only lets pass through 10 to 100 megahertz. So this is high impedance for the output. And we can see that here, this is coming out, it's running into here, there's no current going through there, and this is only going to pass certain frequencies that are really large. So for most of the stuff that we're doing, this works out pretty well, and our assumptions hold true. But as we'll see later on, different frequencies can cause all kinds of issues for us. So different frequencies cause different behaviors. So we say that RL is approximately infinite. If we look at the total gain at this point, we know that GM is on the order of 10 to the minus 3, and we're going to confirm what we said earlier. But our RO is on the order of 10 to the 4th to 10 to the 5th. So we end up with a gain so far of like 10 to 100, which is good, but we can do better than that. Now we're going to take a brief digression into common mode rejection ratio. So we're going to start this off by saying, suppose Vn plus is equal to 2 volts and Vn minus is equal to 1.6 volts. And just as a note, in case I didn't mention it earlier, for our notation, we have little v, big In, because this is AC and or DC that we're dealing with here. So just a heads up. And our VD, we know what this is. This is just the difference between the two, right? So this is 0.4 volts. Our common mode input, and you've probably seen this somewhere else, but if you haven't, here it is. Our common mode input, VCM, we're going to define as 1.8 volts. So the upshot is that if we increase Vn plus and increase V in minus by same amount, we have the following. VD stays the same, and our common mode goes up. All right? And this leads us to define our common mode rejection ratio. We have CMRR is defined as AD over ACM, where V out, capital T, is equal to AD VD plus ACM VCM. So ideally, this is all we care about, but things aren't always ideal. As we know. Okay, and typically we also see CMMR defined. Whoops, I gotta stop doing that. Defined for decibels as well. And to do that conversion, you all should know this by now, and if you don't, memorize it. I am going to assume that you guys know how to convert to decibels for an exam or anything. Oh, good grief. But I will not hold you accountable for knowing how to use this dang pen. Because holy crap, I don't think anybody can figure it out. All right. So there you have it. That's our CMRR, our common mode rejection ratio. We'll probably talk more about this later too. So just put it in your back pocket for now. All right, the common source amplifier stage. So this is where things get really cool. V out. Recall our V out is coming from over here. And coming in. So here's our old V out. We'll call it V out 1. Okay. I can notate that back. I can do it here. And what the hey, we'll do it here too. V out 1. Okay. So we're just tying this guy in to that diagram from prior. And if it helps, go back and look at the block diagram that we created. So V out comes into our CS amplifier and bumps into relatively small capacitance. We've already discussed this. And transistor gate. Okay, we know that. Down the line, a second MOSFET. Hiding in the underbrush. So this second MOSFET has a gate tied back to the gates of our current mirror. And the purpose of this MOSFET down here really is it serves more to act as an active load to the amplifier above. Okay, so you can actually redraw this almost entirely using the simplistic example we had of the common source amplifier. Okay, back when we did that lecture number 5. So this would be our, I forget if I called it RD or RL, but this would be that active load that you can pop in there, and you're good to go. So what we can expect here is a gain equal to minus GM RO4 in parallel with RO8. Because again, we've replaced this, what was a resistor, with a transistor, and so it's going to be based off of the intrinsic properties of that transistor for the resistance, or for our impedance. So this is typically on the order of about 100. So altogether, we should note real quick, note that our AC grounds, in case you haven't been paying attention the last couple lectures, these guys act as AC grounds here and here, right? And this is going to feed into a common drain. Now, recall that this guy we actually got from this equation, minus GM, I'll just rewrite the whole equation, AVI RO RD RL. Okay, we don't have an RL in this case. And our RD here is just replaced by another RO. So it's just effectively two of these ROs in parallel. If these are the same batch of transistors, are roughly equivalent to each other. We have different types here, obviously, but you get the idea for the K value. Then we're going to end up with that equation that we have here. And so I think we need a big color for this. Our big takeaway here is that our overall gain is on the order of 10,000 because we're multiplying 100 by 100 there, right? So I don't know about you, but this is my face when I see it. Great Scott! This is a lot of gain, okay? So something to keep in mind when we're dealing with op amps, they're very powerful devices. But one of the problems that we have now, we've gotten all this gain, but what do we have for our output resistance at the moment? It's not looking pretty, guys. So here's our CS block. If we look at R out, this is equal to RD, which is, RO at this point. So we're not powerful enough to really do anything. Whoops. So we gotta remedy that. Scotty, I need more power. Okay, if you're an electrical engineer and you haven't watched Star Trek, your education will not be complete. You need to watch at least one of them. The original's fine. Okay, I gotta make a quick side note here. So, as engineers, professionally, and as any kind of scientist or anybody employed in a academic capacity for industry or for military or government, the one thing I learned is in that role, always, under promise and over deliver. Okay, and Montgomery Scott in Star Trek actually embodies this really well and was an example for some of my classes when I was in the Air Force. They would cite him for our leadership training. And one of the biggest things that you want to take away, honestly, I swear, is, Scotty, whenever you watch the old Star Trek, he always under-promises and over-delivers. That's the mark of a good engineer and generally a good subordinate, right? You don't want to professionally promise something that you can't or might not be able to do because your supervisor is not always going to understand the circumstances which caused you to fail. So if you can get something that you know is going to work for sure, but you think that you can do even better, hold that reserved even better, and let that be icing on the cake at the end. Don't overpromise and underdeliver ever, because it will hurt you so bad professionally. It will continue to haunt you as you keep going through. Always keep that in mind. All right, tangent over. Like Montgomery Scott, we're going to get more power from somewhere. And although it seems like an impossible task, we know that it's actually quite simple to do because we have our friend, the common drain amplifier. So here we go. This is pretty straightforward. We have our RSS, or our source, and our Vouts. Our final Vout is coming from over here. Our final R out is going to be on the order of 1 over GM. As we saw from our big fancy chart that we made last lecture. And we know from that it's approximately in the order of about 100 ohms. So it's a very low output resistance. And you can really start to see these pieces coming together from that last lecture. We're selectively picking from those different quadrants or blocks in that big chart that we made and saying, hey, I can use some low output resistance right here, and I could use some more current and all these other things. So it's handy to have a chart like that. In this case, we also have R1 equal to R2 equal to infinity because they don't exist in this diagram. We don't have to worry about it. We're plugging in from that other gate. So this goes to, let's see here. The common drain is coming from, oh, I'm sorry. I'm losing my mind today. We're plugging in from our previous output over here. Needless to say, R1 and R2 don't exist in this circuit, so RIS is roughly infinite. And recall that our gain for this stage is kind of close to 1. It's actually, and we should actually write this correctly, less than 1, but close enough. I mean, even if we're looking at, say, 0.8 gain here, we still have overall gain is going to be on the order of, like 8,000, which, great Scott! So, this is a great piece to tack on right at the end there. It's giving us that power that we need, giving us that current. We're getting that low output resistance. Things are fantastic. Okay, so I actually have a lot of time left over here after doing some of the video editing from this lecture that I recorded. So typically I record much longer than an hour. And then I spend a lot of time trying to pare it down for you guys so you don't have to listen to crappy audio garbage or some other random thing that, I started to talk about, or something that's just flat out wrong that I catch in editing where I'm like, oh, there's an error there, there's a typo there, and I have to either re-record it or delete it out. So it's surprising how much you catch after you see it on the first take. You're like, oh man, that's not how I wanted to say that. So in short, a lot of the lectures are going to be, like 50, 52, 50, at most like 55 minutes long, because I'm cutting them back, and that leaves some time left over. In this case, I have a lot of time left over, but my intention is, although you're getting some material cut out from those, I hope to be able to present at least shorter videos that you guys can watch that are optional, that go over the quizzes after the fact, and something in preparation for the final, maybe an hour or two of just working through problems that I think are relevant to the final exam. So hopefully I'll have that recorded a bit in advance of the final so that you have some time to look over it and study. But I think, honestly, for distance learning, office hours suck. There's always difficulties with, the audio connection, and the video feeds are messed up. It's difficult for you as students to show me what you're referring to and what you're talking about. And it's difficult for me to present sometimes. I'm going to try to do it on the iPad and be able to share that screen. But it's not always great. So the more opportunities I can provide for that, the better. But, the trade-off is, your lectures are going to be a little bit shorter. So I hope that's okay. Anyways, let's get into this problem real quick. I know I'm trying to eat up time rambling here. But we start off with this differential pair. And we're going to look at some of this involves our CMRR stuff, i.e. the common mode voltage. And the rest of it is actually working, again, like we did at the beginning of this lecture, from this simple differential pair, this differential amplifier, and then building it into something more robust. So that's what that's all about. Let's have a look real quick inside. Oops, that's the wrong one. There we go. So for the first part, all you're doing for number one, it should be very straightforward, is you're assuming that your inputs here and here are identical, and you're assuming that basically the right and left hand side are identical to each other. That is M1 is equal to M2. And then you just got to show that the currents are the same and the voltages are the same, i.e. that V out is equal to 0. Our V out here is defined a little differently than, what we use in actuality and in, I think, later part of the problem. So don't be thrown off by that. I also want to note, for those of you that have gotten a head start, I'm probably going to delete this bit because I don't think this makes a lot of sense to talk about. Your common mode gain, first of all, I'm not even sure this is the right equation, but the difference here in this particular example where we've set the inputs to be equal to each other, right? This is the AC plus the AC and or the DC component coming in, and if these two are equal to each other, then the DC components will be as well. So this should be a ratio of VCM to, I'm sorry, the output, which would be this top part. That's fine. So it is 0 in the end, but should be over the VCM. And the VCM is not 0 in this case. This is, though. So something's messed up here. So I'm going to fix that, or just chuck it in the bin for that part. Anyways, side note, for those of you that are watching this, later or on time, don't worry about any of that. Okay, when you're solving problems like this, it's very important for you guys as engineers. I know, as a mathematician, we're always just using variables all over the place. And in some instances in engineering, it's important to just use numbers. But when we ask you to show or prove something, 9 times out of 10, you're not using numbers. You should be using the variables and the equations and manipulating them to arrive at the solution. So I see this a lot, especially from computer science, which is fine because that's how you guys do things. Plugging in numbers and trying it and seeing how things work out. This is pretty scientific, actually. But for proofs, we actually have a vehicle for clearly defining what we mean because we've set up our model so explicitly. So use the algebra, use the variables, use the equations. Don't give me, hey, I tried it for 5 and it worked. You'll get very little points for that, unfortunately. So please try to do some algebra. I'd rather see some work in that regard than seeing you just plug in random values and getting something out. Okay. So after you do the sort of, these two things are the same if I put the same thing in, you end up with this problem, which is, hey, let's set one of those equal to 0, prove that this is the case, and work out that small signal model. This is probably the upper limit of what I would ask from you guys on a small signal model type of problem where I ask you to draw it out. Reason being is, it gets kind of complicated down the road. So when we get to, I know I saw it in here somewhere. This guy, this is not going to be on quiz, okay? It might, something like this, almost assuredly probably won't, but could show up on like maybe the final, because the final is going to be a little bit tougher. Probably quite a bit tougher, but it'll be a chance for you to show what you know, not so much to try to stump the chump. Okay, this is not going to be a quiz, so don't freak out like, oh man, I don't know where to put everything. So yeah. This kind of thing, maybe be like kind of the upper limit. This would be a tougher small signal model to build. Okay, you should know how to use superposition to do this stuff. Not too hard once you have the small signal model, right? Let's see here. Same deal there. For this, if you're really getting it, don't worry about doing this. You should see right away that this is just a sign change, pretty much. Without loss of generality is probably, say, W log. Without loss of generality. This is going to be the same basic proof that we did before. Oh, sorry, I'm thinking the wrong one here. Yeah, this one here. This is the guy I'm thinking of. Oop. So this is pretty much the same as what you just did. So you can kind of shorthand notation that. That's fine. For number 7, this should actually be kind of straightforward for you guys. You know, you should recognize what this is doing in here. It's a load, right? We've just represented it with the resistor. So this is just putting together two pieces of equipment that you're already familiar with, which is this common source amplifier and this active load. So yeah, pretty straightforward. And then this is just replaced in here for that. So this is applying what you already should know from the lecture. So yeah, this is I'm a little biased, but I think this one's kind of a fun homework to do because it lets you run through quite a bit of material here. You get to work with that differential pair. You get to build some small signals, and you get to do the you get to do this basic common source deal with an active load on there. So pretty cool stuff. I encourage you to try this out with a replacement or post an example on the Brightspace of, hey, what if I replace this with the other active mode device that we showed in class or in the book? What if I changed this from some other kind of device and put a different kind of load on there? What would the small signal look like for that? How would I connect it in the original circuit? So I encourage you guys to take an active role in your own learning for this because we can't press as much on you guys during the summer, I feel. Because there's just, with it being distance learning and you guys have all these jobs and stuff going on, I don't think it's fair to have hard requirements for, like we do during the semester. We have so much time in between classes and things to really resolve stuff for your harder classes, like this kind of can be for some. For next time, I really would like you guys to review ODEs if you haven't already. If you really are familiar with ODEs, it's going to be a really boring lecture. And I hope that it is. I hope it is the most boring lecture that you encounter because ODEs can be a pain in the butt. But they're really not that bad because they're, the way we're going to approach it is pretty straightforward. And fortunately, since we're engineers, we're going to be doing practical examples where we're using them, which is always great because taking ODEs without practical application, it's really dumb. Trust me, I've been there. Okay, so review those for next time. That should do it. Let's move on to the summary. So, I had to add in one little meme at the end here because this lecture is a lot to digest. Okay, we have a lot of pieces floating around. So I got my fellow kids meme in here for our gain, right? If you want to get all meta with it, this is me using memes to keep up enrollment. I don't know, guys. I'm like 32 years old. I don't know how these memes exactly work. I grew up with like Cheeseburger Cat, and that's about it, okay? So we're just going to do the best we can. Okay, so in summary, we found that we had massive gains. You know what? I'm going to cheat. Here, we got everything we wanted. There we go. We're going to check that we got everything, okay? Yep. Good enough. Okay, so did we get all the things that we ever wanted? We got high infinite input impedance. I've been betrayed. Check. Large differential gain. Oh yeah. Low output resistance. Yep, we just talked about that. And the ability to source at output a large amount of current. Hey, thank you very much. Right here. Yeah, we got everything we wanted. Everything we ever wanted and more. Thanks, op amp. All right, guys, I think that's going to close it out for today. I hope I didn't go over time too much, but we'll see. And thanks to all you guys that are emailing me right now, that are watching the videos as they come out and trying to get ahead of the game. We're going to try to accommodate those of you that are, absolutely cannot make the quiz times. If we get a lot of you guys doing that, we're going to have to adapt. Okay, so some of you contacted me at the beginning. I have like at least a dozen of you now that are in that boat. So we may have to schedule kind of 2 alternate times. I don't want to move stuff around too much, just in case, but we'll figure something out. Don't worry about that. And we'll see you next time. Hope you're having fun. So let's write a little quick thank you. Thanks, op amp. We love you. Okay. All right. Goodbye, everybody.